chip designs are getting significantly more complex. And that means that trying to make sure that they are designed correctly, as well as being operating in the field, is going to be much more challenging. AI can help with that. So, Noam, could you tell us a little bit about your approach that is a bit different from others right now in terms of enhancing a chip implementation and design?
Yes, so we at ProteanTecs, our main focus is to solve the most prevalent challenges for advanced electronics across all verticals. So all of them are now using the most advanced process nodes, automotive, mobile, but most importantly and most exponentially rising right now are AI applications. And in that respect, we've identified the biggest challenges as optimizing power performance, but also guaranteeing the reliability of these very, very complex designs over time. The implications of a failing chip nowadays are very grave because the applications are autonomous driving or very, very large language models recommending stuff to you. So our approach is really a two-pronged approach. We're going to provide software solutions that will actually uh, provide recommendations, insight, and actions for a chip to cover those challenges I just mentioned before
Mhm.
throughout its production, as well as while it's running in the field. And this software will be based on a very unique set of hardware monitors that are embedded in your chip. Okay, and together these solutions where our software reads out these agents during their production, their ramp up, their high volume manufacturing, but also while they're running in the data center in the car, will allow you to optimize power and performance and also guarantee reliability over the lifetime of this product to meet its specifications.
So that means that from a chip designer's standpoint, you're going to be involved with the initial chip design and giving them essentially the IP for your agents that are going to be on the chip. The question I have is, what are some of those agents going to be, and what type of work is required from the developer to figure out where these things are going to be placed, et cetera?
All right, so I'll start from the types of agents. So it's important to mention again this novel approach where we're providing a solution and not just a tool. The underpinning monitors, we call them agents that we embed, will cover many different physical facets of a chip while it's running and while it's being tested. Some of them are more recognizable, like process, voltage, and temperature, but others are more novel. And the reason is that we want these monitors to feed into we want the monitors to be able to allow us to follow through on these applications that we're intending to provide. So aside from process voltage temperature, we have monitors that will look at workload, stress over time, at slack or margin of timing to failure of millions of paths, which is a very unique proposition of noise modulated on certain paths, of clock jitter, etc. And again, all these monitors, the point of them is not to provide a standalone insight to the user, but to feed into these software stacks that will eventually follow through with these applications. With respect to implementing in the chip, you're right. We have to, the idea is any chip designer of this kind of a advanced chip would engage with us. We
Mhm.
would provide the collateral of these agents to embed into the chip, but it's not that alone. We have a full implementation suite that we provide for the ease of implementation, but also in order to get the right agents in the right areas of the chip to maximize its performance post-silicon.
Okay, to follow up on that, obviously there may be dozens to thousands of these agents on a particular chip, especially as they're getting extremely large. How do you determine where these are going to be placed? In other words, what's going to be monitored, and how many are you going to have? Is that something that's going to be laid out based upon, standard chip designs, or is it something that's going to be very specific to a particular design?
It's actually customized to your design, and that goes to what I explained before, this unique and specific implementation suite that we provide. It's we call it the Proteus EDA, which plugs into your design flow, your
Mhm.
design and implementation flow. And in that context, we will also analyze your design, and according to our analysis, plus certain heuristics that are relevant to each type of agent, we will recommend which agents, how many, and where to connect them in the chip. And eventually, we'll also provide a hardware monitoring system which interconnects all these agents to local controllers and from local controllers to a main controller so that the access, control, configuration, and readout of these agents is all done very simplified from one central point.
Okay. Well, now that you have the design in the chip and you have access to it, uh, the first time you're going to be able to make use of this is once the chip is finished with production. What kind of support are you providing at that point?
Right. So, as a matter of fact, the first value that we provide would be as soon as that chip comes back from production. So as soon as it's on at wafer sort, and it's connected to electricity, so to speak, you can read out our agents and get value. And the value that we provide by our software, it'll be different software stacks throughout the production life cycle and in the field. At each stage, our software will provide different insight, different value that's relevant for that stage. For instance, when that chip comes back from production, the first thing you want to know is perhaps what bin it would be associated with, if it is potentially a defective chip. We have a very high resolution way of monitoring outliers in order to screen them out earlier. And then when we move on to high volume manufacturing, we have ways to predict the VMIN per chip in a very individualized manner and very, very quickly. And then further on, once we get into the field, we'll provide other software and other value, which is more relevant to be running in the field, which would be, for instance, performance and or power optimization or health monitoring over time by giving a health score at every single time during its life cycle.
Okay. Now, what type of cycle time or is there any additional feedback from the agents in real time, especially when you're in the field? Is this something that you periodically have to go through and check, or is it something that can be notifying the software?
But everything really depends on, this is the solution-oriented approach that we have on what you're trying to achieve. In the field, most of the applications that we are providing have to do with having very low latency responses.
Mhm.
If I want to be able to customize the power or performance to the exact situation the chip is in right now, with respect to environmental conditions, but also the precise workload that it is running right now, then my monitoring and my actuation have to be very low latency, and it has to be practically real time.
Mhm.
Therefore, our firmware will be engaged with reading our agents out at real-time frequencies and providing that response fast enough for the voltage to be regulated in that workload span.
For an application, say in a data center, you could have a very sophisticated host and a lot of software that's going to be able to do things in real time. What about applications that might be in the field, say a self-driving car, which may not necessarily have connectivity to the cloud? Is it
That's
something
exact
that could be implemented in a controller that is on the car itself?
completely. That's it. That's again back to the what is the problem we're trying to solve, and that is a problem, connectivity from the car. And therefore, we have applications like real-time safety monitoring, which is all enclosed in firmware. There's no need for interconnect to a cloud. We realize that that would be a challenge. It is able, with a very small footprint, to process the agents while it's running in the car, in the ECU, in the vehicle, and provide a health score there and then. So that, for instance, one of the outputs would be to the driver on a dashboard. We've assessed that this product will be failing very shortly according to our grade. Please drive it to the service station as soon as possible.
Okay. What type of functionality is required in that type of controller? Is this something that's going to be a very small micro, typical application processor, or does it need to be something more sophisticated? And does it require, say, AI acceleration to do that, or is it something that doesn't necessarily require heavy lifting in that space?
So we're trying to implement these particular applications, the real-time ones, in firmware, and hence we are limited in processing power and memory in order to get it into firmware. The more the applications rise to a more compute heavy and memory heavy requirements, then we can get more done there.
Hmm.
But the one that I just described to you now will actually run in firmware and do its own logic, and that's where our secret sauce comes into play. How do we do that processing across thousands of agents to get you insight and do that all in firmware?
Hmm.
Um, but the result will be only in firmware, and it will be a score so that the existing monitoring systems in vehicles nowadays, for instance, health monitoring systems that look at many other things, will get a new input, a new signal called chip health or system health that comes from within the chip. And it will be able to use that as yet another input in deciding what to do, what the status of the vehicle is and what the next action is.
Okay. Well, that's fascinating. Now, obviously, there's a lot of data that's out there. Is this something whereby once particular issues are identified, that you can collect additional debugging information that can be then passed off to, either people that are working on something like a car or passed up to the cloud to be assisted by other people that are going to be able to analyze the data?
Completely. This part is super interesting also because in our solution for starters, we're expecting our customers to be using, as I mentioned previously, our solutions from production, from first chip and back from the fab, all the way through characterization before launching into the field. Therefore, they have a lot of data already pertaining to that chip in their labs. When an issue arises in the field, we're very much collaborating with our customers to record that data and be able to compare it. This is a practically, we're hearing from our customers a new capability where they get supposedly field problems from, it could be from a vehicle or it could be an RMA at the data center level, and they have factual concrete data to compare apples to apples because they're looking at those same agents before they were released and after they were released with a full history behind what happened to them. It's a novel way of dealing with the return material.
So that sounds very interesting. Can we see this in action?
Yes. So on the right, you can see the measured voltage from within the chip at different locations indicated by these different colored lines. The red threshold at 800 and at 585 millivolts indicates the VDD min at last pass. The 650 millivolt threshold here in green reflects the the same VDD min plus all the various voltage guard bands needed to accommodate the worst case scenarios mentioned before, like aging, temperature, workload, etc. On the right, you can see those margin agents, those white dots illustrated in the previous screen, all measuring over time the margin of the pass that they're monitoring. The multiple margin measurements are indicated by the overlapping gray lines that you can see over here. The y-axis indicates margin, x-axis time. The black line indicates the worst margin of them all. We can see that due to the guard banded voltage of 650, the measured margins are high. There's a lot of slack. Even the lowest one of them all, the black one, has a significant amount of slack. The red line over here, by the way, is the timing margin for the VDD at last pass. So that means when timing will start failing, and you can see the fair amount of slack over here. The AVS Pro firmware application leverages this visibility to lower the voltage until the timing margin is minimal, yet safe. Let's see how that looks. When I enable AVS Pro, we're going to see under the hood the AVS Pro firmware directly voltage regulator to reduce voltage until the margins reach a place which is optimal with respect to saving power, but still safe enough to recover from slack requiring events. So here we see that the voltage was at the direction of AVS Pro reduced to 620 millivolts. At that point, the AVS Pro stops directing the voltage regulator to reduce the voltage. The margins are now lower. You can see them across the board, yet even the lowest one, the black line, is still at safe enough level to recover from slack reducing events that may happen. At this voltage level, you can see we're saving around 9% of dynamic power. If and when any of the events mentioned previously that require to increase the voltage happen, we will see the resulting drop in margins. So if we do that, we're going to see the margins drop. Below a safety threshold, margin agents trigger an interrupt for the fast protection against timing failure, usually via clock stretching. And in parallel, the AVS firmware will redirect the voltage regulator to a new optimized voltage value. In this case, directed them back up to the original 650 millivolts. After some stabilization time, the AVS firmware will redirect or direct again the voltage regulator to drop the voltage to a safe margin point. To summarize, we've seen now how the AVS Pro can use the deep data of real-time timing margin of the most power and performance limiting paths to optimize the voltage of a particular chip at every instance.
Oh, very good. It sounds like a fascinating approach and one that I think is going to be very valuable to companies and developers. Thanks for filling us in.
Thank you very much.